so today we're going to be covering a general overview of signal processing that we'll find in commercial music production. We'll talk specifically about dynamic processing, frequency processing, and we're going to read the transform as a topic by itself. Let's go on now. Okay, an overview of signal processing. In the commercial field, when one is talking about signal processing, it is referred to in the business as an effect. So anytime you hear the word effect, you basically look at it as being signal processing. Now the first question to ask yourself is, should you approach it from an analog or a digital direction? Okay, digital signal processing is cheaper, more accurate, and it's always the best approach. If this is your attitude, you will be like this very, very quickly. The real world, especially in terms of music production, is, on to the next one. Okay, your real world considerations dictate a judicious use of both analog as well as digital processing techniques. Now, as I mentioned yesterday, over the next couple of days, we're going to run across some approaches and techniques which, any way you look at it, are going to be really rather bizarre. And the reason for that is, in the field of music production, we have aesthetic and commercial considerations which dictate things which go contrary to what you would normally think that would be conventional wisdom in terms of an engineering. Okay? Yes. Okay. Now, real-world considerations dictate a judicious use of both analog as well as digital processing techniques. Now, before I go on, I'd like to say something about what your position here is all about. You are not here to passively take in whatever I'm giving you. That's not what it is. I want you to look at the next 2 days as being analogous to being in an art class. Okay, right up here before you, I'm going to be placing some object, some model, maybe a person, maybe a bowl of fruit. It doesn't matter what it is. And you are the artist. You have to interpret what I am giving you. Now, here's the kicker. Some of you may be in oil paints. Some of you may be working in pastel. Some of you may be working in clay. Some of you may be writing a poem about whatever I'm doing up here. You are all different. In this class, we have people who are musicians. You are really wanting to get maybe clearer ideas what would be going on in the studio and real world. Maybe some of you have aspirations of starting your own music studio. And then you have to try and decide what things you want to implement in terms of hardware versus what you want to implement in terms of software. Perhaps you're students and you're basically thinking, okay, what am I going to be doing after I graduated in another couple of years? You may find yourself having to be sitting in some company someplace and modeling or emulating technologies that you maybe never even thought about before today or tomorrow. And that brings up another consideration. If you are going to be implementing things in software, then you have to decide whether, several things. First of all, whether it should be implemented in the time domain or the frequency domain. We touched upon that yesterday. And a general rule of thumb is if you have to do something which must be executed in real time, like let's say you, in another couple of years, you students go to work and you're working on hardware boxes, to do this process or that process, and it has to be in real world, in real time, you'll probably find that everything you need to do has to be done in the time domain. Meaning in basically take your samples and you manipulate your samples right there. On the other hand, if you're working inside of a computer and you may find that you don't have to actually work in real time, then some of these effects can be implemented in the frequency domain, which would basically mean you take your samples, you divide it into small hunks, frames, windows, whatever you want to call it. You perform your Fourier transform, transfer everything into your frequency domain, which is actually two data sets. data set. So it'll be a phase spectrum and there'll be a frequency spectrum. You do whatever it is you're going to do to it, and then you have to convert it back with the reverse Fourier transform back into the time domain so that you can do whatever you're going to do. Now, a general rule of thumb is that if you have to do that, you probably may not be able to execute it well in real time because those are computationally extremely demanding. So what I'm going to be doing here in the next couple of days is presenting a lot of things before you. I'm going to be presenting some things that would actually be insane to try and implement in a hardware fashion, but you pay attention to them even if they are antique technologies, because they may be antique technologies, but they are not antique sounds. If you find yourself having to program effects in an effects box for some XYZ company, and you're going to sell these things across the world, you better be able to walk into that company and say, yes, I know what this technologies are all about, even if they have not been used in hardware in decades. That's something to keep in mind. Okay, let's go along now. Next one. Let's look at the advantages of implementing these things in an analog format. First of all, it is a natural sound. I put natural in quotation marks because natural is in the ears of the beholder, and because for so many generations people have heard it in this form, it sounds natural to them. So you automatically know that you will have a broad public acceptance of whatever these effects are. But there are very strong cons when it comes to analog implementation of effects. The first of which is it's frightfully expensive. Whereas you can pick up a lot of software plugins for free on the internet, and even if you have to spend money for them, they're usually not that much. Hardware implementation of effects or signal processing can get to be very expensive very quickly. Another thing is that inherent to an analog approach to processing is that you tend to have questionable signal-to-noise ratios. And then they're also limited in scope, meaning that if you have a compressor, it's just going to be a compressor. If you have a reverberator, it's just going to be a reverberator. So these are one of the things to keep in mind when it comes to implementing an effect in an analog way. Let's go on to the next one. Digital. It's inherently inexpensive. Well, it's much easier and theoretically cheaper to distribute software than it is to distribute hard boxes. Okay, they can be windowless in scope on your digital workstation. You can load it up with a gazillion effects without spending a lot of money. On the other hand, one of the major cons about a lot of the digital processing used in production work is it tends to have a bite to it. And as such, public acceptance is always questionable. Bite. Well,
how far do you go? How deep do you go in the sampling? The bite is still there.
There are a lot of things. Yes, so when it comes to the various sampling as well as quantizing, these introduce a particular bite to it. But there are other things as well. For instance, if you're going to do something that involves any kind of granularity, funny things happen. Usually not good things. But that's something I really want to talk about tomorrow. But sometimes this bite is inherent to the solid state electronics, which is the default state behind everything nowadays. And I'll get more into this later, but basically there tends to be a bite to a lot of digital stuff, which comes back down at some point to the very way in which we will break things into blocks. But yeah, that is a good question. Any other questions? Yes. Yes. Well, actually what I mean is like if you have a digital audio workstation, you can sit down and you can be downloading effects plugins all night, okay? You can exhaust yourself of hundreds of free software plugins. If on the other hand, if you wanted to do the same thing about in hardware, you'd have to be a good laptop or something just to afford it, you know. But you can sit down and anybody can download 100 or 200 software plugins to the digital audio workstation with no trouble, especially if you have a rather, shall I say, pragmatic view of intellectual properties. Okay, but good questions. Any other questions? All right, let's go to the next one. Okay, where do we apply this? Let's look at the next slide, please. All right, now if we go back and return to our overall signal chain, which started at the microphone in the studio and ends in the speaker or headphones of the consumer, you have a chain. We obviously are not going to be concerned about the consumer side, we're going to be concerned about the production side. Next, please. This is something that should be burned into your mind. Absolutely burned into your mind. You may want to take a picture of it, you may want to do something because this is really key to the whole thing. Now, what we have here, this is a basic breakdown of what our production is going to be all about. It starts with the microphones. I have about 50 or so microphones at home. We have the analog section, which can be, in the minimum, it can just be a small interface or a small mixer, and it can be a large mixing console with a lot of outboard analog processors. It can be as expensive or as big or as simple, but there's always an analog section. We have our digital audio workstation. These would be things such as Logic or Adobe GarageBand, or what there's many digital audio workstations out there. These interact with our plugins. Now the plugins are essentially effects. Rather than have effects as standalone signal processing software, the way the business works is a plugin is something where it is meant to interface with an existing package. It has to exist with any number of things, like Logic, for instance. So you have a lot of businesses out there whose only purpose is to program effects. And we'll program them for any of the number of the packages on the market. Now here's an interesting thing a lot of people don't really realize. The digital audio workstation itself, the high-end ones, have the ability to interact directly with outboard hardware processors. In other words, if you've ever used something like GarageBand or Logic or any, how many people have worked with a digital audio workstation? 1, 2, 3. Okay, you know that within your digital audio workstation, you have the ability to insert virtual effects in your signal chain. Okay, well, the higher-end digital audio workstations give you the ability to insert in your signal chain hardware processing. It basically goes out through your digital to analog converter into your hardware processor and then back into it. But it is inserted in the signal chain of your digital audio workstation. Is that clear? Now, the bottom line for all of this is your signal processing can occur at every one of these stages, every one of them. And your decision into where you want to implement things can have very profound impact upon what your final product is going to be. Any questions here? All right, now everything we're going to talk about in the next couple of days is predicated upon understanding this basic layout right here. So I cannot overemphasize this. Let's go to the next one. Yes? Yes? They will be filed. They'll be filed in whatever format. I mean, whether it's under CDs, whether it's just digital files. Yes. Yes. Yeah. Right. In other words, what you do is you come in here, you come into your digital audio workstation, you record something. Of course, it's recorded digitally. Whatever you've done here, of course, we'll leave that discussion later. So it's recorded digitally. But like, let's say you have a choice. between putting in a software reverberator, or let's say that you're fortunate and rich enough to have one of the older plate reverbs. Well, if you're rich enough and fortunate to have one of those, when you're processing that, you go into your outboard plate reverberator, mix, master, mix and everything you're going to do. It comes back in here, and your effects have been, your analog effects have been applied to a digital file. Got it? All right. Any other questions? Yes. You can have a bunch of digital effects. You can have 1,000 digital effects in your machine. In the business world, it's very, very competitive. You have to have something to differentiate yourself from your competition. And the analog effects is really where, in the real world, where most people will differentiate their production house from another production house. It's a business consideration. And there really, in many cases, there are some things that really do not implement well digitally. And so since some things still do not implement well digitally, there's probably for a long time going to be great demand for analog processing. But that's a very good question. Have I addressed it? Okay, the bottom line is if you want to put food on the table, you got to give the customers what they want, and your clients like analog processing. Okay, let's move to the next one. Now, overall, we have to think in terms of how we implement an effect. In general, an effect can be directly in the signal chain, and you understand, if I'm talking in the digital domain, we're talking about a virtual signal chain. This is still a way to think of it. An effect can be introduced directly in the signal chain. It can be a side chain, or some effects can only be implemented on an entire file at once. We'll get into that. Let's look at an example of this. This can only be implemented in the digital domain. The easiest example would be normalization of a file. All right, you cannot normalize a file in an analog way. You know how you take your sound, you put the normalization, you bring it so that whatever your peak is to wherever you want it, usually 0 dB. That's an example of an effect that can only be implemented digitally. These others can be implemented either digitally or analog. Now, if you're dealing analog, the distinction between these two is going to be hardwired into it. But if you're looking at it in a virtual domain, in terms of software, these things tend to become blurred. Let's take some very simple, trivial example. Let's take attenuation, for instance. The easiest thing is to simply take your file, if you're doing it digitally, take your file, apply some scaling factor to reduce it, and then send it on the out. But something like attenuation can also be affected in a side chain. For instance, if you have your main signal coming in here, you could also send the main signal to your effect here, which in this case would be nothing more than inverting the phase, applying some attenuation factor, and then feeding it back in. Because the phase is inverted, you can attenuate a signal using a side chain. That's a typical example, but the important point of all of this is that when you're dealing digitally, the distinction between these three approaches can sometimes become a little ambiguous. And that should not be a problem. It really just accentuates the fact that you have a lot of things that you can do. The whole field is wide open to whatever you want. Any questions? Okay, let's go on to the next. All right, we're going to talk about different classes of signal processing. What we're going to talk about over the next couple of days: dynamics processing, frequency processing, time-based processing, and pitch-based processing. Next one. We're going to start with dynamics processing. Now, as I said yesterday, what I'm going to do, we have different backgrounds here. Every time I start a new topic, I want to start very, very simply. I'm not trying to insult your intelligence. I'm just trying to acknowledge the fact that different people in this room have different backgrounds. Okay, next one. Transfer characteristics. Okay, when we're talking about dynamics, we're essentially talking about when something is loud, when something is soft. We're looking at this is inherently a time domain approach to processing things. Next. All right, let's just start. Whether we're talking about something virtual or real, let's look at a simple buffer amplifier. In which case, whatever goes in is what comes out. Now, there's a lot of real-world reasons why we need to do this in hardware, but I don't want to talk about it here. But let's look at the transfer characteristics of this. Next one. If we look, we're placing our input here. This it would be the way we describe our transfer characteristics. This is what the important thing is I want you to pay attention to. And this would be the output. Now, the important thing to remember about, we're talking about voltage transfer. In the real world, if we're talking about black boxes, these two need not be the same. It could be, one could be current, one could be voltage, one could be something totally different. Let's say air pressure. For instance, let's say this is changes in air pressure, and this is changes in voltage, in which case we're looking at a microphone. And we'd be talking about the transfer characteristics of a microphone. When there are drastic differences between whatever we're putting in and whatever we're putting out, this is known as transduction. Now again, some of you may be very, very familiar with the concept, and to others this may be new, but this is what transduction is all about. It's using very, very, very different inputs and outputs, but all flowing through a transfer characteristic. Now the thing to note here is notice the slope. We're going to see that that's going to be important as we go on. The next. First, let me stop. This is all clear to everybody. This is okay. Now, let's look at an attenuator. An attenuator, basically, we have our signal, either virtual or real, and we have an output, and we have it being reduced. Now, let's go ahead and look at the next one. Now, if we look at the transfer characteristics, we see the slope is like this. So we have our input, we have our output, and the two, you see that the output signal has been attenuated. Now, we would not normally consider an attenuator or amplifier or anything like that as an effect, but we're just taking step by step into where we're going to be headed. Let's look at the next one. Let's look, the opposite of an attenuator is the amplifier. We have a smaller signal on the input, and it becomes a larger signal on the output. Next signal. If we look at our voltage transfer characteristics, we notice that it has this slope. All right, the next one. Now, let's look at a compressor. In a compressor, if we put different signals in, what the compressor does is it can take the lower signals, it can amplify them, but at the same time, it can take the louder or stronger signals and it can attenuate them. This affects to reduce the dynamic range of whatever our input signal is. That's the next one. So what we see, the way a compressor works, is we have an active transfer characteristic going on. It responds to whatever block of signal that we're wanting it to respond to. Now we're starting to talk about real effects. Let's go on to the next one. There are different flavors of compressors. A simple compressor, which is pretty much what I just illustrated earlier, as the ability to take the softer signals and boost them, take the louder signals and reduce them. Smaller signals and bring it louder, louder signals and bring it smaller. That's the typical compressor. Now, we want to do this for very real musical reasons. How often have you had your iPod and everything like that, and you're going on and you're running around town, and you have this song that's very nice, except it's annoying in one point. You know, when it becomes so soft, you can't hear it because of the traffic noise. Then when the song becomes loud, it's painful to your ears. That's an example of a situation where the producer should have put some more compression in. In the old days, compression was required because of technical reasons. There was a very substantial noise floor in any product, and by the same token, your peak, your loudest point, was very much limited by the technologies of the day. So in those days, compression was absolutely essential because of the state of technology. And today, compression is absolutely necessary because of the state of our lifestyles. All right? Any other questions about this? About the compressor? The expander. The expander is a compressor that works in reverse. It again has a dynamically changing transfer characteristic, but instead of taking the softer signals and enhancing them, and the louder signals and reducing them, it works in reverse. It takes the softer signals and makes them even softer. It takes the louder signals and makes them even louder. Now, the expander has a very, in contemporary, basically the expander doesn't have much use today. Old analog noise reduction units used to be based upon this concept, but they pretty much have gone the way of the dinosaur. However, some people still like to use expanders if their style of listening to music is to sit down, sit in your easy chair, in your living room, have a nice Johnny Walker or whatever chemical, recreational thing seems to fit your lifestyle, and listen to the music. Because since the music is almost always compressed in the production process, you can sometimes get a more natural sound if you expand it back in your living room. But there's not much use today. Automatic gain control. There's not too much difference between the automatic gain control and the compressor, except it's a question of why you're doing it. The automatic gain control was most used in the days of the old cassette recorders, when whatever you put in it, it would just do a rough job of bringing everything to the same level and putting it onto your tape. But I believe it's still, even with your little cell phones and things like that, I believe they tend to have automatic gain controls on it. Right? The gate. And radio, yeah. Radio, yeah. The gate is another thing we need to look at. The gate is a particular type of, it's a particular type of dynamics processor that basically it will not open up. It clamps everything down until the input signal reaches a certain threshold, at which point it opens up. Historically, the gate was used in multi-track recording situations in order to negate the background hiss of all the different tapes we have. But you'll find that gates are still very useful today if you want to process signals to make them more intelligible. Like, let's say you've recorded some speech in a somewhat noisy situation. It can become much easier on the ears if you apply a gate to it, which would mean that whenever a person was talking, it would open up. When they stopped talking for a bit, it would clamp down so you don't hear all the background noises and cars and whatnot. So gating still has a use. Now we have the limiter. The limiter is a form of compressor where it behaves in a very linear process right up until the time that a certain threshold is reached, at which point it does not allow any further level increase. Now, one of the things that is important is all of these things have different ways of looking at the signal to decide how they're going to act. And the limiter, by its very nature, responds to the peak values of the signals. So these are the different flavors of compressors. If you have any type of digital audio workstation, compressors are some of the things that will come with any of them, all of them. They have different flavors, different parameters, different sounds, but it is a very, very basic form of dynamics processing in any type of production work. Questions at all about the compressors or gates or anything? Anything? Okay, very good. Let's go to the next. Wait, something isn't right here. Okay, let's go to the next one. Saturation. Everything we've discussed so far has been based upon an ideal concept of dynamics processing. Now, the real world tends to impose itself. Let's go on to the next one. In the real world, imagine an amplifier. Imagine the amplifier has a voltage gain of 100, and let us say that we're putting in a 1 volt peak-to-peak signal in. So we're going to get 100 volts out, right? No, we're not going to. I mean, we're going to be limited by whatever the internal power rails are from whatever the device. Even if we're dealing in an entirely digital domain, if we're dealing with integer numbers, at some point they saturate. Okay? So saturation is something that is ubiquitous to just about any kind of processor we have. In this case, we put a signal in. The attempt of this amplifier is to want to go in a full excursion, but internal limitations because of the power availabilities cause it to clip. Let's go on to the next one. Saturation. We do not need to worry about saturation because it is simply the result of the misuse of the amplifiers that we designed. Huh?
Engineers.
Engineers. That's an engineer's approach to the subject. Okay, the next one. Wrong. Okay, because we're not talking about engineers, we're talking about musicians. And never underestimate the ability of musicians to mess things up from an engineering standpoint. Okay, let's go into the next one. Let's look at this amplifier. Okay, this would be a very typical amplifier that guitarists would use. You also might want to note the sound, the device here. Okay, let's go on to the next one. If you look at the specs of this, there's this nice little phrase here. This amp is excellent at emulating the response and sound of a tube amp. Now, if you buy a Lamborghini, does it have a switch that allows it to imitate a VW Bug? No, it doesn't. So here we're talking about something that is very, very important and will come up again and again and again. All right, let's look at the next one. This is another amplifier. This one has tubes in it, has valves in it. Look at the price, about nearly 3 times as much as the other one. Okay, we're spending about 3 times as much for an amplifier that, from an engineer's standpoint, should be an inferior device. Okay, this gets us back to what we were talking about, the aesthetics and commercial considerations from what we were talking about yesterday. Let's go on into the next one. This amp, did I put the same one there? Okay, the next one. Ah, yes, here we go. This is the magic device of anyone involved in professional music production. It is the vacuum tube. It is what is your friend. It is why vacuum tubes will not go out of manufacture. They are your friend in terms of any production environment. Okay, next one. The vacuum tube is the benchmark for what music is supposed to sound like. This is true. It has become the benchmark of what music is supposed to sound like because for 100 years, this is the way people have heard it. And if you don't give the people what they expect to sound, then you're not going to be very good at production. Next one. Okay, as I said, this is what people have been listening to for 100 years. The next one, please. All right, now, let's compare the solid state to the vacuum tube to get some ideas about technically and from a psychoacoustic standpoint of what is going on. A solid state amplifier will saturate like this. There is a hard saturation. Let's look at the voltage transfer characteristics. All right, it behaves like this. It's extremely linear and is what from an engineering standpoint would be its operational zone. But we're talking about musicians. The operational zone for musicians is very different. So once we exceed it, we have a very, very hard clipping. Now what this does from a psychoacoustic standpoint is this generates a lot of odd harmonics, and people do not like odd harmonics. It's jarring, it's unpleasant, it's fundamentally something that people do not like. Let's go to the next one. I have no idea what it said. Odd harmonics. Yes, 1, 3, 5, 7, like that. Okay, so if you look at the harmonic structure series, okay? So it produces a lot of odd harmonics, and people don't like odd harmonics. Now, okay? Next one. Now, this is the way a vacuum tube amplifier will saturate. Instead of being a hard saturation, we have a soft saturation. Okay, let's look at the transfer characteristics of that. Now, the transfer characteristics show a noted lack of linearity in its main operating range. The result of this smoothing out of its transfer characteristics is what gives us smoothing out here. Now, when you saturate soft like this, it generates a lot of even harmonics. People like even harmonics. You remember that, was it at the beginning of those films with that TDS, with that, the wah that comes up? You've seen all those films? That is an example of what happens when you take a person and you give them a lot of even harmonics. It's something that's thrilling. It sets the mind, it's like the right masala in your food, okay? It's just that good, nice stimulation without being unpleasant. Okay, the next. All right, so now, what we have here is a concept known as tube compression. Now, we have a signal like that, but the output signal comes out like that because our peaks have been rounded out. You have an overall reduction in the dynamic range, and this is the main thing that's behind tube compression. It's partly a question of compression, but it's also partly a question of acting like an exciter, which I'll talk about later. Any questions so far? Okay, very good. Oh, before we go further, go back. There's something else I want to talk about. There's one aspect that I'm going to talk about now, but I didn't really know where to put it. If we compare two amplifiers, one is based upon tubes, and one is based upon solid state. When you make any kind of solid state device, when you manufacture any kind of tube, there are always going to be variations in the performance. You have a batch of this stuff coming out, and there's going to be a lot of variations. That's just the way any manufacturing process does. So that when you make any kind of amplifier, you have your input signal, you have your output signal, but you always put a little negative feedback in order to stabilize things. That'll be true whether we're dealing with solid state devices or whether we are dealing with vacuum tubes. Now, the kicker is, when typically most of your solid state devices have gains in the thousands, while your vacuum tubes generally have a gain which oftentimes is no more than 100. The result is it requires much more negative feedback to stabilize a solid state device than it does to stabilize a tube device. Now, all this is fine and dandy in theory. In theory, it allows our designers who design the whole thing to control the characteristics and not let it be up to the vagaries of the manufacturing process. But there's one problem. There is a very small lag, a very small time lag in all of these devices. There's not much, but it's very small. But the result is the very large amount of feedback used to stabilize a solid state device compared to the much smaller amount of feedback required to stabilize a tube has the effect of, at the lower frequencies, the phase relationship is as it's supposed to be. It clamps down on the gain and everything's fine. But the problem is that as the frequencies become higher and higher and higher, the phase relationship starts to become one where you start to get regeneration rather than degeneration of the signal. Now, then they will do all kinds of fancy little tricks, to try and keep that under control. But the result is, inherent to the solid state device is whenever you have a transient, like from a drum strike or anything like that, they become exaggerated through the solid state device. Whenever you have any quantizing error, it becomes exaggerated through a solid state device. So earlier, I wanted you to ask about the bite. Well, partly this bite comes to a combination of a mismatch between a solid state device, and the nature of the digitizing process. Does that answer the question? Okay, let's move. Yes? Yes.
The issue was the same. When you say that there was saturation and the upper paper and the lower got cut off.
Yes.
This image.
Can you back up a little bit?
This image, if the input is quite high.
Yes.
The
If it's high enough, if it's high enough, then it will resemble, if it's high enough, basically, your signal is just going to look like this. If it's high enough. But the way most musicians tend to operate these things, they tend to operate them in a musically acceptable level of saturation rather than a hypersaturation. But yeah, your point is quite correct.
so who will define the middle part of it?
Whichever band member is paying the money. That's the truth. They will determine, if we're talking about the same thing. The level of saturation is usually going to be determined by musical requirements. Okay? It's only adjustable in the sense that you can, I see your point. Let's talk about the guitar amplifier, which is where this is, which is most used. In a guitar amplifier, you have a preamplifier, you have a power amplifier. This is the classic arrangement. So what happens is, you can take your preamplifier and turn the gain all the way up, and then you have the clip signal coming out. You can turn the input gain all the way up, but you can turn this gain down as long as you want. You can have a very soft signal, but one which is highly saturated due to the fact that your preamplifier is overdriving your power amplifier. Does that answer your question? Maybe not. Then maybe I'm not understanding the question, I don't know. But the point is, it is an artistic decision. You can determine at whatever stage of the game you're imposing saturation, you get to determine how much it's saturated.
We have the processor with the guitarist might use it.
As I said, the guitar has the knobs on the amplifier. You crank up the amplifier of your preamp, you crank up the gain of your preamp till you get a delightful level of saturation. And then you have your power amplifier, which is loud or as soft as you want it. If you don't want to have any saturation, you can keep the preamplifier level low, but you can keep the power amplifier level high.
It would be the same way the guitarist will produce distortion in the guitar.
No, this is exactly this is it. This is how guitarists do the distortion. And they decide by the way they set the preamp versus the power amp what level of distortion sounds good to their ears. Okay? Yeah. All right, next one. Tube compression. As I said, I just talked about tube compression and this. Okay, solid state versus valve comparison. Your solid state devices, the pros, excellent linearity. The cons is the hard saturation, which we just discussed. Your vacuum tube, your pros are soft saturation, which gives you an abundance of even harmonics. The cons, of course, is poor linearity. That's just a summation of everything we've been talking about. Okay, now I think that we're about to leave. Okay, let's go on to the next subject. Okay, so the bottom line is the vacuum tube is probably the most popular form of analog signal processing on the market. Is that clear to everyone? Now one thing, alright, let's go on to the next one. But valves are not always implemented well. Yeah, this is an important consideration. Next one. If you look, this is an example of, I believe, is a preamplifier. Notice it has a blend, a tube blend. Anytime you see anything like that, stay away from it. It's the sort of thing that everybody and their dog knows that vacuum tubes are good, but everybody and their dog doesn't really know when it's implemented well. You have a lot of products on the market where they put vacuum tubes in it for no other reason than to sell it. They may be very, very poorly implemented. If you have the vacuum tube directly in your signal chain, you have no wiggle room. You better get it right. But if you're just going to stick the vacuum tube as a side chain processor, then you have not the same pressure to get it right. So this usually, if you see the sort of thing, it usually means just a piece of crap. Just a piece of crap. Just stay away from it. That's not a good implementation of a vacuum tube. Next one. Okay, now I'm talking vacuum tubes, but I know a lot of you guys are into programming. Pay attention because you may find yourself having to be emulating vacuum tubes. You may find yourself working for a company and they're going to say, okay, we need you to emulate our vacuum tube as far as its effects. And you say, yes, I know how to do it. So keep this is very important. All right, now let's look at some real world examples. This is a very nice little microphone preamp that's on the market. One of the less expensive ones that I feel is good. You can find cheaper ones that use vacuum tubes, but usually they're not very good. This is one of the cheapest ones that I've seen. It has a very good implementation of vacuum tubes. This is a preamplifier. Next. This one is also a preamp, similar price range. I've not actually worked with it, but it seems to probably be pretty good. Next one. Okay, now this one is a vacuum tube based compressor. One of the best ones I've seen. It didn't actually say vacuum tube, but it is. Let's go to the next one. Okay, before we leave our topic of dynamics processing, are there any questions over this? Yes? It's very common to mix them both. It's very, very common. It depends on what you want to do. The vacuum tube is basically a signal processor. It's an analog signal processor. But yeah, it's not unusual to mix the two. Next. Okay, frequency processing. This is the next thing we'll be discussing today. All right? Okay, now there's two types of frequency processing common. There's a manipulation of the harmonics that's already there, the content that's already there, versus another type which is a creation of spectral content which is not in the original. Those are the two things we will be talking about next. All right, now I'm going to go to some very basic stuff. So for you people who are double E's, please bear with me. For those of you who are just getting into this, this is for your benefit. Okay, now what we have here is essentially we're talking about filters. We have our ability to talk about high-pass filters, low-pass filters, notch filters, and band-pass filters. Now, you will have to emulate these in software. So this is also something to keep in mind. Next. I know you know, going to go over it anyhow. Next. All right, let's get down to the basics. From an engineering standpoint, the range of human hearing is said to extend from 20 hertz up to 20,000 hertz. That's roughly about 10 octaves. Most of our hearing, most of the stuff we're dealing with will be in the middle range. The next. Okay, if we have a black box filter, and let's say we put in some pink noise into it, and if we have a bypass filter, it's just whatever goes in is what comes out. If we have a high pass filter, at some point we have the lower frequencies attenuated while allowing the high to pass. The low pass is the opposite. We have the lower frequencies unattenuated, but it attenuates the high frequencies. A notch filter just simply has a very narrow frequency band, which is attenuated, and the band pass is the opposite, where we have a particular band which is attenuated. This is basic stuff, but necessary for understanding the next few slides. How do we implement filters? Okay, next one. This is your first stage of frequency filtering. Whenever you decide on what your microphone is going to be, you have to be concerned with what is with what its frequency characteristics are. What is its linearity? which in microphones, there is no such thing as really a linear microphone. Your measurement microphones come closest to it, but that's the closest. This is going to be your first stage of frequency filtering. Next one. This is what a very typical microphone's response will be like. If we look here down at 20 hertz, if we go up here to 20 kilohertz, we see a tremendous degree of variation. We see, what are we looking at here? We're around 18 dB of range between here and here. 18 dB is a lot of variation. That's an awful lot of variation. Okay, so use your microphone selection very well, because your microphone selection can determine whether you sound good or don't sound good. Next one. This is your second line of filtering. This is your console. Next one. If you look in the console, in all these gazillion knobs, you find a repetition of your equalizers. In this example, we just simply have a 3-band one. We have our high frequencies, mid frequencies, and low frequencies. On my console at home, I use 4. Some consoles have 5. Okay, next one. If you need more than your console gives you, you can always use your outboard equalizer. This particular one is called a graphic equalizer. The reason being, the next one, is it presents a graphical representation of the way it behaves across the audio spectrum. Next one. Another type is the parametric equalizer. One of the problems you oftentimes have with the graphic equalizer is a lot of times you find yourself trying to work between the knobs. That can be very awkward. You can get around that by using an outboard parametric equalizer. The next one, where you have different parts of the audio spectrum, will give you a parametric EQ where you have the control of the center frequency. You can move it this way or that way, your bandwidth, or the degree of boost or cutting of your signal. And you may have 3, you may have 4, you may have different numbers, but that's the way a graphic equalizer works. It's a little less intuitive than that's the way your parametric equalizer works. It's a little less intuitive than the graphic equalizer, but actually much more powerful. The next one. Note, just because an EQ is rack mountable, you must not presume that it is an analog device. Some of them are digital. These are defined, but I feel that if you're going to use them in recording, you might as well use the software equalizers in your digital audio workstation. Let me emphasize the word software. As I said, you may find yourself programming them. Okay, next one. Okay, your third line of filtering is your software filters. One of the things to notice that in most cases, and virtually every case, your graphical user interface is imitating those of your analog devices. That's just the way musicians think. That's the way recording engineers think. So familiarizing yourself with the analog devices is going to be the first thing you have to do if you're going to be programming them in software. Next. Okay, now, generation of spectral content. Essentially, this class of processors are called exciters, but sometimes the word exciter is used in a more narrow sense. What this type of frequency processing does is rather than manipulate material which is already there, this generates material that was not there. Okay, let's look at the next one. The thermionic valve, the vacuum tube that we had mentioned before, the very nature of its soft saturation generates harmonics that were not there in the original. So this is one type of very fundamental exciter. Next. Other than the vacuum tube, most harmonic synthesis is done with software. That's where you guys would come in. Next. Okay, one thing that we can do is tube amp emulation. You can get tube amps software really for free. There's so much of it out there. Whereas anything that's going to cost you, anything that you get in terms of real implementation of vacuum tubes is going to cost you some money. It's going to cost you a pretty penny. So a lot of people use tube amplifier emulation as a way of getting the sound without having to deal with the expense. Next. Tape emulation. Now, tape recorders also have a traditional classic sound that many people want to deal with. And although there are high-end studios where you go from your digital audio workstation into the tape and then out of the tape back into your computer, that's really not a practical way for almost anybody. So if you really want the classic tape sound, which many people do, you're going to get it through tape emulation. Next. Bit crushers. Okay. What the bit crusher is, you know, when you have sampled, you're all familiar with the concept of quantizing and sampling, right? Everyone here is? Come on. Why feel shy? No. Oh, okay. Well, when we take a signal, we have to do two things. We have to sample it. We have to quantize it. So when we do that, we get basically, if we sample it and put it out, we get something that will look like this. Something on my drawing isn't very good, but you get the idea. Okay. So in other words, you get a signal that looks like this. So quantizing error is the error in this direction. Sampling error is the error in this direction. Now, back in the 1980s, people were dealing with a lot of samplers, which were devices, and they had a particular crunch to them because of the technology of the time was such that there were extreme amounts of both sampling error and quantizing error. Now, that initially, of course, was seen as a limitation, but it defined a certain aesthetic feel. So, like if you're really wanting to get into some grungy, a lot of punk stuff that will give you a lot of, and you want that drum to have that quantizing crunch. You can take your signal and artificially you can reduce both the sample size or the quantizing size. You can make it sound like an 8-bit sample when you may have recorded in 24 bits. So that's something very desirable in certain genre of music. That's what the bit crush is. Now, by its very nature, the introduction of quantizing and sampling errors introduces harmonics, which is not there in the original. Next. Subharmonic synthesizers. So, well, the purpose of the subharmonic synthesizer is to take your lowest component and generate some content which is lower than that, usually an octave. This can give you some bottom, this can give you some richness in your productions that otherwise may be a little bit weak on the low end. Any questions? Okay, next. Exciters. And yes. I'll draw it close very quickly. Okay, let's go into the next one. The transformer is a very important thing. The bottom line is nowadays there's been a reduction in the number of transformers in the signal path from the whole process. So a lot of times we want to introduce more of that. Well, thank you very much. Goodbye.